Swayam Prabha. Digital India. Educated India.
Good morning. Once again, I welcome you to this course soil mechanics, and last few classes I have discussed about very preliminary on shear strength, background only I have discussed. Now, I will discuss really on soil shear strength of soil, and what I have gone through as background, and we have mentioned that when there is a at a particular point inside the mass, because of the externally applied load, we can see that at a point state of stress, and of course, initially we have seen in 3-dimensional form, and then we discussed in biaxial form, because this is very commonly we use for soil mechanics, though we can use in the 3-dimensional, but initial understanding with 2-dimensional biaxial problem can be handled first. And while doing that, when it is a biaxial problem, then we have seen that if you know the state of stress in that respect with x and y direction, what are the components, then we can find out also any other plane what is the normal and shear stress, and also we could find out there is a plane or orientation of a plane or a plane oriented in such a way that on that plane principal stress, maximum principal stress occur, or in some plane maximum shear stress occur, and now that also how at which angle or which plane that happens, that also we have discussed. And finally, in summary, we have seen two things, one is principal plane, another is principal stress. And what is principal plane? That is a plane that is acted upon by a normal stress only, is known as a principal plane, and in that plane obviously there is no tangential or shear stress present. Okay. And similarly, principal stress, that is a plane, first of all we have mentioned where the maximum normal stress occur, that is a principal plane, and principal stress is the normal stress acting on the principal plane is referred to as a principal stress. And at every point in a soil mass, applied stress system that exist can be resolved into 3 principal stresses that are mutually orthogonal, and the principal planes corresponding to these principal stresses are called major, intermediate and minor planes. That means, the plane on which maximum occur, that is major principal stress, the plane on which a minimum occur, that is called minor and plane on which the intermediate stress occur, that is called intermediate plane. And major, intermediate and minor planes and are so named from the consideration of the principal stresses that act upon them. That means, larger stress acting on a plane, that is major, a smaller one, that is a minor plane, and the intermediate one is the intermediate plane. The principal stresses sigma is known as the major principal stresses act on the major principal plane. Okay. Okay. So, the major principal stress sigma is known as the principal stress sigma is sigma 1 actually is known as the major principal stress acts on the major principal plane. So, there are 3. So, where sigma 1 acting, that is major, and where sigma 3 is acting, that is minor, and where sigma 2 acting, that is intermediate. Okay. So, this is the way we generally classify. Next, and you can see this one. This is the plane, this is the sigma 1 is the major principal stress, and this is the direction of major principal stress. So, major principal plane must be perpendicular to that. So, if this is the major principal stress, then your this one will be the major principal plane. Similarly, this is the sigma 3, that is minor principal stress, and so minor principal stress will be acting perpendicular to that plane to that direction. So, minor principal stress is plane is this one. So, if the direction of stress is this, then direction of the plane will be perpendicular to that, or if the plane is defined, then normal stress will be perpendicular to that obviously. So, if I know the major principal stress, that is also normal major principal stress or major normal stress, major principal stress, that is a normal stress. So, that means plane will be perpendicular direction. So, that is the way it is defined here. Similarly, if you have any plane here like inclined here, on that plane what is the if the plane is oriented like this plane is rotated, and there is a new plane suppose, then what will be the stress on this, we can calculate whatever way we have discussed previously. Now, this is the one we have shown before also, the shear strength, that is your at this point, suppose at this point what is the shear and what is the sigma, that we can find out by this equation, and obviously this is the initial form we got, but this form also can be trigonometrically simplified, and it can be written as sigma x minus sigma y by 2 cos 2 theta minus tau x y sin 2 theta. So, this thing this form, this is whatever is the trigonometrically, if you simplify you will get this form also. Similarly, this is the initial form we have got by considering equilibrium. This is also another form of the sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta minus tau x y sin 2 theta. So, this is again trigonometrically if you simplify you will get. So, these and these, whether these or these they are same, and these and these they are same, only thing is this is expressed in double angle, and we have mentioned that whatever angle we will see in the circle, on the plane actually half of that. So, this is the plane, suppose if I imagine the 2 theta, actual orientation of the plane is theta. So, that is the thing we have already learned. So, the same thing I am just will apply to the soil. So, these are the initial expression, and this is in this other important things are shown. If I draw a Mohr circle here, on this Mohr circle, this is actually major principal stress sigma 1, this is minor principal stress, and if I take a point here, suppose point D, then that is a plane, either this is the plane, suppose if I consider on that plane what is the normal and what is the shear, by using this equation one can find out. So, limit conditions, that means so you can see I have already explained this, that maximum shearing strength resistance is developed when the angle of obliquity equals its limiting value phi. So, maximum shearing resistance developed by the soil when the angle of obliquity is equal to phi. So, when this the angle, it was different angle and the circle is there, suppose, and this circle initially you will have this angle, then this angle, like that, when it will just tangential to this, that is the limiting condition, and that condition actually alpha become phi, the angle of obliquity equal to alpha f equal to alpha phi. That means, the maximum shearing resistance developed when the angle of obliquity equals its limiting value phi, and for this condition the line OD becomes a tangent to stress circle inclined at angle theta to axis OS. So, that is actually I can show you in the next one, you can see you can see in this is the circle, and this is one thing. So, this is the circle actually, this is circle, and on that circle when this alpha will be changing and it will become tangent to this, at that point only we will get the limiting value, the limiting resistance. And so, with this observation another further observation will be done, that is you can say oh sorry. You can see that is another interesting point that arises from the figure, that the failure plane is not the plane subject to the maximum value of the shear stress. Suppose if I draw the Mohr circle here, and suppose this is the origin and maximum shear stress is occurring here, but this is tangent somewhere here. So, it is not, that is the point, interesting point that arises from the figure is that the failure plane is not the plane subjected to the maximum value of the shear stress. So, at this plane that point is not maximum shear stress, maximum stress is acting here. So, the criteria of failure is the maximum obliquity, not the maximum shear stress. So, that means the how much oriented or rotation or orientation of the angle, that plane, that is important than the maximum value of shear stress. They are of course quite close, but not really to the maximum value. And if phi is assumed constant for a certain material, most of the soil material we will show you later on that your phi value for a particular soil, a definite value of phi will be there. Again if you change the condition, the phi value will change, the same soil, but still for the time being suppose all conditions are same, and for a particular soil phi is constant, suppose if I consider, and then the shear strength of the material can be represented by a pair of lines passing through the origin and O at angles O plus and O minus to the axis O x. Suppose you can see this is the axis O x, and plus phi minus phi, this is phi, that line I can draw tangential to this. And so, if this is the one, then to the axis these lines comprise the more strength envelope for the material. That means, what is the meaning of it? That means, the strength envelope, that means along the failure, if I consider sigma and tau, if we change, then failure will take place, whatever failure, those points will be within that only. And state of stress represented by circle A is quite stable. So, that is other two observation is you see, suppose I have drawn, this is the for a particular soil, the phi is constant, suppose if I assume, then this is failure envelope, this is the orientation, actually we know the maximum. So, if I draw a circle tangential to this, that means it is just at the verge of failure. Whereas, if I consider another circle which is also representing the state of stress or location of the state of stress at some condition, state of stress, and this is the one at a particular point state of stress, if I plot and if I get this circle, that means the soil is much stable, and whereas it is just stable, if I change little, failure will occur, and this is actually much below the stable condition, much better than the stable condition. Similarly, if I stress the material in such a way, the Mohr circle become such a big one. Okay. So, it is going out of the envelope, that means it is totally unstable or it will be failure. So, that means to have the soil a stable condition, that more circle should be within this envelope. That means, if I draw from the origin with plus phi and minus phi 2 lines, the circle should be within that 2 envelope. So, that is the thing, state of stress represented by circle A is quite stable, as the circle lies completely within the strength envelope, that is inner circle. Circle B is a tangential to the strength envelope and represent the condition of recipient incipient failure, that means middle one which is tangent, and the circle C cannot exist as it is beyond the strength envelope. So, that means that is failure. So, this one is a failure, this is just verge of failure and this is a very stable condition. Now, relationship between theta and phi, that is orientation angle theta, the plane oriented theta, and phi is the angle of internal friction. From this is the thing, actually we have to now find out the relationship, and that relation, for that relationship we can take the help of the diagram, that is in the this one you can see this. I can consider a triangle, I can consider this triangle, and then from this triangle, if this is 2 theta, then this plus this will be theta, and again this and this is same. So, this and this angle will be theta. So, this is theta, this is theta, and so by based on this observation I can formulate this way. You can see DCO is 180 minus 2 theta, angle DCO D and DCO, this angle 180 minus 2 theta, because this total is 180. So, 180 minus 2 theta, this angle, and your in triangle ODC, angle DOC is phi, ODC is 90 degrees, DOC is a phi, DOC is the phi, and and your ODC is 90 degrees and OCD is 180 minus 2 theta. ODC is 90 degrees, you can see ODC, this is actually since a tangent and this is radius. So, this angle will be 90 degrees. So, this is 90 degrees, this is phi, and this is 180 minus 2 theta. So, if that is the one, and this angle sum to be summation should be 180 degrees. So, phi plus 90 plus 180 minus 2 theta will be equal to 180. Is it okay? 3 angles of a circle of a triangle, if you add, then it become 180 degrees, and that 180 degrees, and we have seen 3 angles, one is phi, another is 90 and another is 180 minus 2 theta. So, then this one if you simplify, you will see theta equal to 45 degrees plus phi by 2. So, this is the one. So, this is if this is the plane, actually this is the plane and failure plane, and this is phi envelope. So, what is the relationship between the failure plane and the angle of internal friction? So, that is theta equal to 45 degrees plus phi by 2. Now, we have discussed about shear strength, and we see that one is actually phi, angle of internal friction. We have that phi we have discussed, and now it is a cohesion. It is possible to make a vertical cart in shields and clays, and for this cart to remain standing unsupported for some time. This cannot be done with dry sand, which on removal of the cutting implement will slump until its slope is equal to the angle known as angle of repose. So, that means, in a silt and clay, suppose this is the one, but you can make some cart. Suppose if you make an excavation here, up to some depth it will stand without any support, but if it is a sandy soil, suppose this is a sandy soil, and then if you try to excavate, then it will actually this slope will fail and it will have some final inclination. So, this cannot be done with dry sand, which on removal of the cutting implement will slump until its slope is equal to an angle known as angle of repose. That means, the soil will form an angle which is equal to the angle of repose, which is nothing but equal to phi. In silt and clays, therefore, some other factor must contribute to shear strength. That means, silt and clays where sand is not able to stand, whereas silt and clay is able to stand. What is the reason? The reason is that silt and clay also possessing something that is some other factor must contribute to shear strength. That is what, and this factor is called cohesion. That means, when the dry sand, the shear strength contributes from the angle of internal friction, that is phi, whereas in silt and clay there may be phi. In addition to that, there is some other parameter which actually can help to stand unsupported, that is because of the presence of cohesion. That means, cohesion also contribute to the shear strength. Now, you can see that shear strength, this is actually, if I plot, this is as a sigma. We generally plot one axis is sigma, another axis is tau, and then your failure envelope typically will have this form. There will be intercept here, that is equal to the cohesion, and this is this inclination will be phi. And obviously, this the C and phi if you have, then it will have a definite equation and shear strength equation, and that shear strength equation can be written in this form. It can be seen that the shear resistance offered by a particular soil is made of the two components of friction and cohesion. That means, as I have mentioned, that some soil may contain or may possess only the friction, some soil also may possess only cohesion, and most soil actually may possess actually both the component actually cohesion and friction. So, that means, total shear strength will be coming from the contribution of both shear, friction and cohesion. So, that is the one, that two components of friction and cohesion, and friction resistance does not have a constant value, but varies with the value of normal stress acting on the shear plane, whereas cohesive resistance has a constant value which is independent of normal stress. That means, because of this shearing resistance from friction, it depends on the normal stress. If the normal stress is more, the shearing resistance will be more, normal stress is less, shearing resistance is less, whereas shear resistance contribution from cohesion is constant independent of any normal stress. So, because of that, we can finally write the expression tau shear strength of soil at any point will be equal to C plus sigma tan phi, where tau f is the shear strength at failure and C is the cohesion and phi is the normal stress, and phi sigma is the normal stress and phi is the angle of shearing resistance or angle of internal friction. So, now there are three typical thing can be there when particular soil C equal to 0, that is sand. In that case, your tau will be equal to sigma tan phi, and another soil can have phi equal to 0, that means clay. For that, tau will be equal to C only, and if the soil possesses both, that means phi and C, then this is the general equation for shear strength. And shear strength depends upon effective stress and not on the total stress. So, I have discussed again the total stress, effective stress, and that time I have mentioned that the effective stress is very important, particularly because the shear strength depends on very much on effective stress only, and Coulomb's actually more Coulomb's equation therefore modified, that whatever equation we have given before, that is Coulomb more Coulomb equation of shear strength tau equal to C plus sigma tan phi, that can be modified in terms of effective stress parameter, that tau equal to C prime plus sigma prime tan phi prime. So, these are all called C dash is called the effective, C dash and phi dash is called effective stress parameter, and phi dash is the sigma dash is the effective stress acting at the point where we are calculating the shear strength. Now, we can see we can see a general form of shear strength Mohr circle I can take, and in this Mohr circle you can see that the suppose failure envelope is this one is the failure envelope, which is having a phi and there is a value of C, and based on this, and this will be sigma 3 and this will be sigma 1. Now, we can relate this sigma 1, sigma 3, phi and C geometrically. So, let us consider this one, and I will see that in the next slide. This is you can see now that sin phi, that means we can sin phi in the previous one, sin phi if I consider this is actually phi, this angle is a phi, this angle is a phi. So, if I consider sin phi, that means I can this triangle I can consider, and based on this triangle sin phi equal to actually this is 90 degrees. So, this by this, this by this. So, this C D by C O dash. So, if that is the case, then sin phi I can write in those in terms of some known parameters. So, this is how much up to this how much, up to this how much, all those, and this is what all in terms of that I can express. So, sin phi equal to d c by O dash c, as I have mentioned, and d c will be you can see half sigma 1 minus sigma 3. This is d c is the radius, d c is the radius. So, it will be half sigma minus sigma 1 minus sigma 3, and O dash c will be k plus half sigma 1 plus sigma 3. So, k is what actually we have shown here, k is taken as this much. So, this plus this, and this one actually half sigma 1 plus sigma 3. So, that means I can sorry. So, half sigma 1 minus sigma 3 I have done half sigma 1 minus sigma 3 and k plus half sigma 1 plus sigma 3. This is the sin phi if I express in this form it comes. So, if I simplify, then it becomes sigma 1 minus sigma 3 by 2 k plus sigma 1 plus sigma 3. Then if I take in terms of sigma 1 minus sigma 3, which is known, suppose sigma 1 minus sigma 3, if I express sigma 1 minus sigma 3, that will come 2 k sin phi plus sigma 1 plus sigma 3 sin phi. And if I go back to the previous figure, then we will see that k which we have noted, that is actually c cot phi. Suppose this is the diagram, and so this is the k actually, and this is actually phi, and this is actually c. And so, from here I can write k equal to c cot phi, k equal to c cot phi. Okay. So, this is the k. So, this k actually c cot phi. If I substitute c cot phi in this equation, then sigma 1 minus sigma 3 become 2 c cos phi plus sigma 1 plus sigma 3 sin phi. So, this is a very generalized expression of in terms of relating sigma 1, sigma 3 and phi of the soil. So, and this when I have written this equation in terms of actually total stress. Similarly, the equation can be expressed in terms of either normal stress as given above or in terms of effective stress as given below. That means, we can express the in either total stress form, that is the one which without prime. So, this is the equation, and if I express in terms of effective stress form, then I will get this is the equation. So, now so these two important expression sometime will be useful. As I have mentioned in the beginning, that there are a number of field and laboratory tests available, and from the test from the we apply certain amount of normal stress, and then we apply we shear the soil, and then at the time of shearing what is the stress we can find out, and then if we have those values, and based on those values we have to find out the shear strength parameter C and phi. So, we measure generally this and sigma 1 and sigma 3 during test suppose, and then if I do at least 2 tests, then I can express this equation. Suppose one is sigma 1 1 and another is sigma 1 3, that is one set, and based on that I will get this equation in terms of C and phi. But since C and phi will not change, the same soil we are testing identical sample, again I will suppose another test I will do sigma 1 2 sigma 2 2 sorry sigma 1 2 and sigma this is 3 1 suppose 1 1 3 1 and this is 3 2. So, this is another set, the same equation I in terms of this I can express, since C and phi will unchanged. So, from the two equations by solving I can find out C and phi. So, this is the way actually this is what actually, as I have mentioned before, that we need some theoretical background along with the experimental data to understand the shear strength. So, that is the one application, that whatever we have found out now relationship between C and phi and C phi and the normal stresses, the major and minor normal stresses, whatever relation we have got, and experimentally if we get some data correlating them, we can find out the value of C and phi of the soil. With this I will stop here and I will take next. Thank you.